And this is, there's really very little new math today at all. The math that we're going to do, the algebra we're going to do is going to look very similar. It's going to be almost the same stuff we've been doing. If we look at a circle, okay, let's just take a circle centered on point C with radius r, and that's what we've got in this picture here. So if we do that, we're going to say that the coordinates of the center are h and k, and let's take two other points. Let's take a point A and a point P here. Okay, what kind of triangle is that? Okay, how come? Study that for a second. Tell me why maybe that's a right triangle. I'll make that bigger. So what do you think? Look at the coordinates. How come? Kristen, what do you think?
It's because the bottom right coordinate has a K from point C and an X from point P.
Ah, okay, yeah, look at that. If you look at the coordinates here, what do you know? If the coordinates of C are HK and the coordinates of point A are XK, the Y coordinates are the same, aren't they? Right? So they have to be horizontally aligned. Agreed? Okay. Compare the coordinates of points A and P. The X coordinates are the same, right? And so they have to be vertically aligned. And so by definition then, horizontal and vertical are at right angles, aren't they? So that's a right triangle. Okay, so if that's true, then what can you tell me about these two distances? How would you describe the distance between C and A and P and A? What would they be? If they weren't horizontally and vertically aligned, it might be a little bit tougher, right? Not horrible, but the fact that they line up horizontally and vertically makes it pretty easy. What do you think? How far apart are A and C? Because that's really all this means, right? Going back to geometry, if I write 2 points in a row like that with no symbol over the top, what's that stand for? Distance, right? Length of a line segment or a distance. If I put a symbol over the top, then it becomes, so this is a measurement, right? Remember this from geometry? And if we put like if I put a line segment over the top, that would indicate it's a segment, right? If I put a line symbol over the top, it would mean the line through those points, etc. But if I just have two endpoints, we can call them, of a segment, then that stands for the length of that segment, right? So what is that?
Would you do like x minus h?
Yeah, that's all it is, isn't it? Just x minus h. The k values don't change, do they? Right? If an ant were to walk from C to A, his y value isn't changing, but his x coordinates are changing from h to x, right? And so we could call it x minus h, okay? Now, if this had to be something that was always positive, and distances are always positive, yeah, how come I might want to do that? So it's always positive. Good. In this picture, it looks, the way I've drawn this, it looks as though it's already positive, though.
By KAB, do you mean, I mean CAB, do you mean CAB?
Say it again?
No, it's the distance.
No, it's just
At the triangle.
where it says
That's triangle. Yeah, is triangle CAB a right triangle?
She's actually trying to CAB.
Oh, yeah, you're right. I got you. I got you. It is. Thanks for the translation. I didn't catch that. So, why might I want to put those absolute value bars there? It looks like it's already positive.
If the triangle's on that side.
Ah, okay, yeah. Because really, these points, when we say something like P has coordinates x, y are variables, aren't they? Right? So those could change, right? This point, we should be able to freely kind of move this point around, like pretend it's a bead and we're sliding it around a hula hoop or something, right? We should be able to slide this thing around. And as we do, the location of this point is going to change with it, right? But it could have just as easily have been, for example, maybe right there, right? That could have been point P with coordinates x, y. in which case this would have been point A, right? Does that make sense? So yeah, we probably want to put absolute value bars around that. So what about the length of segment PA? Y minus K, okay? And once again, we want to ensure that that's always positive. So what could we do? Absolute value bars, something like that. Okay, so if that's the case then, let's put all this information together. What's going to be the length of segment CP, which is an important segment? Why is that one so important? Because it represents the radius of the circle, right? So what's that going to be? We know this is a right triangle. You told me this is a right triangle. All right, so let's go back to this page over here for a second. Maybe we can see it bigger. So we know that's true. How am I going to find the length of that segment if I've already found the lengths of the other two segments? Yeah, it's just Pythagorean theorem, isn't it? Right? So what's that going to look like then? I guess I could start off by saying, why don't we make CP squared, and then we can square root both sides if we wanted, right? Let's just say, what's the length of CP squared by Pythagorean theorem? Okay, so CA squared plus PA squared, and we know what those are, right? So I've got the absolute value of x minus h squared plus the absolute value of y minus k squared. Can I simplify that in any way? There's something, yeah, let's write that in the easiest, least constrained way that I can. What about those absolute value bars? Is there anything I can do with those now? Okay, if it's going to be squared, okay, any real number squared is positive, isn't it? So do I need to make those positive? I don't, right? And that you'll see that's maybe the first time you've seen that, I don't know, but that's going to happen a lot in math, right? Sometimes we have to define quantities as being positive, but then in an expression, maybe they have to be positive anyway, like if they're being taken to an even power, and so I can omit the absolute value bars, which you would, I think everybody would agree, that makes it a little simpler, doesn't it, right? So then we end up with about something like this. CP is really just R, isn't it, right? Yeah. And so this is the equation that we get, right? Well, we never specified what X and Y were. What X and Y are, did we? Right? So this is completely general, right? This is the relationship that should work for any point on this circle, right? We said we could slide this bead any place on the circle, couldn't we? Right? So think about what an equation means for a second. If we go back, let's remind ourselves just kind of conceptually about what this means. If I've got something like, let's just take a line, take something really simple. If I've got the line y equals x plus 2, we all know what that looks like, right? I can graph that. That's just a line with a y-intercept of 2, slope of 1, so it's just going to look, there's 2 points, connect and extend. What does that mean? What does that equation do for us? How many points does it describe? An infinite number, doesn't it? Right? Every point on this line is, in a way you could think of it as being produced by that equation, right? But maybe even a better way, we talked about this at the start of the year, is that every point on that line is a solution of this equation, right? It's an ordered pair that satisfies the equation. For example, we have the point 0, 2. If I plug in 0 for x and y for 2, I get a true statement, right? If I plug in 1, 3, 1 for x, 3 for y, I get a true statement. Those are convenient ones, but there's an infinite number of choices, right? There's an infinite number of choices, but they are related by this equation. I can't just randomly pick a point. That point's not on the line. I can't pick a value of x and y randomly. I have to pick, if I pick a value of x, let's say I want to say x equals 11, well then I would have to figure out what the exact corresponding value of y is to fit on the line, right? Plug in 11 and solve for y. Agreed? Okay, so this is like a locus of points, we'd say in math. It's a set of points that fits this one exact relationship. That's a pretty simple one, but that's a relationship too, isn't it? Right? In this relationship, x and y are variables. What about h and k and r? What are those? Not really. Those aren't variables. They're a little different. Like if I took the general equation of a line in slope-intercept form, m and b really aren't the variables, are they?
No.
Those are, once I pick a line, m and b are fixed. Agreed? For this line, you told me m was 1 and b was 2, right? Once I dial in those values of m and b, I've got exactly one line. So we'd say that those are in math, to put a technical term on this, and this isn't really in the book, but you guys are beyond the book. We'd say those are parameters. Okay? Those are values I can set to identify one specific line out of all the infinite possible lines, right? So in the same way, aren't h and k and r parameters? What do they stand for? M and b stood for slope and y-intercept. What do h and k stand for? Not radius. They've defined that point. What's unique about that point right there? Ah, it's the center of the circle, isn't it? Right? So h and k are what then? The coordinates of the center, right? So that's important. If we want to pin down a specific circle, we need to be able to identify where its center is probably, right? And then r, what's r? Radius. Right? So in the same way, we could define a specific circle by just pinning down where its center is, hk, and what the radius is, right? But x and y then are the variables, right? Because once I've pinned down a circle, how many points are there in that circle? Infinite number, right? And what's true about all those points? Well, they all have to satisfy that equation, right? Yes, ma'am.
So is it always the variables minus the parameters?
Yeah, I mean, that's the way we write it. Technically, would it really make any difference? I mean, because we're squaring it anyway. It's really not going to make any difference, but yeah, that's always the way we do it. Yeah, okay. Does that make sense? Does that make sense? So if we picked a specific circle, like let's just say we said, and this why is this general, right? So that's kind of what we're talking about. If I pick a specific circle, if we say something like x minus 2 squared plus y minus 3 squared equals, let's say, 3 squared. The values of x and y that would fit on that circle are the ones that would satisfy this equation, right? If I were just to take, like if I were to pick, say, 100 random points, values of x, and solve for y, what I would get is just kind of like a dot arrangement where I'd start to create the circle. As I created more and more random points, those dots would start to look more like a solid line, solid ring around the radius, right? But you get the idea, okay? So this is our standard, whoops. This is our standard form, we'll say, equation for a circle, all right? And where did it come from? You know, I think you're going to forget this at some point. You know, when you move on to other things in math for a while and you forget about circles, you come back to them, you'll forget this. But you could always derive it pretty easily. How? How could you recreate that for yourself? Yeah, with this simple picture. That's how I think you got to do math. I think you do math with pictures. And the picture contains a concept. And then you can always go back and, you know, really pretty quickly recreate what the relationship is. I forget stuff all the time. But I can remember these pictures pretty well. So I can always go back and, what's it take, 30 seconds to go back and think of what develop for yourself what the equation is going to be. Okay? All right, so start easy here. On your scratch paper or on your notebook, just try that. We'll warm up a little bit. Write the standard form equation of the circle with center at the point 7, 4 and with radius 6. So what do we get? No big deal, we're just plugging in values, aren't we? It's like plugging in M and B. What do we get?
X minus 7 squared
Plus,
squared.
and how would I say that? I'd say, how would I say that? The quantity x minus 7 squared plus quantity y minus 4 squared equals 6 squared, which is what? Okay, make sense? Okay. That's a pretty convenient way to write this. When you see an equation like that, you can immediately pick out what the center is and what the radius is, right? Everybody agree? Okay, but what about something like that? What are we gonna do there? I want you to think about that one a little bit. It might help to just sketch a little picture. Doesn't have to be accurate. Try that real quick. Just sketch a picture that would include those 2 points within the context of the circle. Doesn't have to be exact, but where relative to the center would that point go? Left or right? Left, up or down? Down just a little bit. So maybe something like right, doesn't have to be, but something like right there. One thing we do know though is it's contained on the circle, right? So it's gotta be on the hoop somewhere, right? So how could I come up with an equation of this circle? What are the essential ingredients? We need 3 parameters for a line, M and B, or just 2, sorry. 2 parameters for a line. We need 3 for a circle though, don't we? We need both the x and y coordinates of the point, of the center. And what else do we need? How am I gonna get the radius?
1, 2 minus y1 over x.
Yeah, that's no big deal. I just, by Pythagorean theorem, right? And distance formula, one and the same. I could just define a little triangle here. Like so. And there's the radius, right? What's the length of this side? How'd you get that? 16 minus 8? Yeah, just difference in, I never put the coordinates there, did I? So this is 8, 4, so that's just the difference in the x coordinates, right? And then what, 1? So the radius is going to be what? Square root of 65, right? Square root of 8 squared plus 1 squared. Where do you see that? So 8 squared plus 1 squared is 65, right? If I square root both sides, that's my radius. So then what would the equation of that circle be? Okay, so x minus h plus y minus k equals r squared, which is 65. Okay, no biggie, right? Okay, once again, not too bad, right? Because even though we weren't directly given the radius, it was pretty easy to find. And so that's a pretty easy way to express our answer. Okay, what about something like that though? That's kind of a mess, right? If we went back to, let's just go back to this one for example. If I were to, that's in a nice, convenient standard form, but what if I expanded that algebraically? I multiplied everything out. What's this gonna give me? If I expand out x minus 7 squared, I'm gonna get x squared minus 14x plus 49, good, plus, what about this one? Plus 16 equals 36. And then what if we just kind of rearrange those terms, put all the constants on the other side, or maybe even just put them all on this side, but combined like terms. I could get something like x squared plus y squared.
It should be 8y.
What'd I get wrong? Oh, 8y, yeah, you're right. Plus y squared minus 14x minus 8y. 49 and 16 is what? 65?
Yeah.
Minus 36 would be what? 59? Or 29? So I could write it like that. That's not as good though, in a way, is it? You can't just see what the coordinates of the center and what r is in that case, can you? Right? But sadly, sometimes that's the way, when we do algebra, for example, and we collect all our like terms, you might end up with something like that. And then the goal is to write that as a circle, right? So what could we do if we wanted to reverse this process? If I wanted to say we just started here and we want to get to there. Any ideas? What could we do? Okay, we could move the 29 to the other side. Okay, that's a good idea. Right, so move this over here. Let's just kind of think about our steps first. So we'll move that over there. Now what? Okay, so maybe we could collect the x's together and the y's together, right? So let's go ahead and do some of this stuff. So we'll collect the x's. So we get x squared minus 14x. And if we collect the y's, we get y squared minus 8y. And then the suggestion was we push the 29 over here. That's a good idea.
Oh, what's that one?
Yeah, this is starting to maybe look a little bit like Module 3, isn't it?
Just squared.
Ah, okay, yeah. Everybody agree, we could just complete the square here, couldn't we? Right? Because our goal is, look what we're trying to do with this. We're trying to get all this stuff to look like that, aren't we? Right? We're trying to coax the x terms to conspire together to turn into a perfect square trinomial so that they'll factor into a perfect square, right? Perfect square factors. And same thing with the y's. Right? And then whatever's on the other side is just going to be a number, right? And so that's going to end up being r squared. The square root of that number will be the radius, right? Okay, so we already know what we're going to get, but let's go through this process now. This is a little more complex in a way, just because we got two of these things happening at the same time, but really it doesn't make it that much worse, if at all. So what's this going to become? We know that we want to pick a value here. Whoops. Pick a value here. And I have to add that to both sides, don't I? So that this is going to look like that, right? Perfect square. And then I need a plus sign there, don't I? Plus. I got to pick a value there and add that to the other side as well. So that this trinomial that I create becomes a perfect square trinomial that factors into a perfect square. And then I'm just going to get some number on the other side, right? So what's our order? This is good review for the Module 3 stuff. What's the order in which we fill in these blanks then? Let's work on the blue stuff first. Yeah, so we know that, right, we know the first thing we want to do is whatever's there, so step 1, half of that, right, half of b is what we're going to combine with x in our perfect square factor, right? So minus 7. Now step 2, square it. Yeah, whatever's there, we're going to square. This is going to get kind of messy. And that's step 2, isn't it? So negative 7 squared is 49. Add that to both sides. And then just repeat those with the greens, right? So what number is going to go there? So that's going to be, and now the last step is, step 3, is combine all those. So negative 29 and 49, well that's convenient, that's 20, right? Plus 16 is 36. What do you know?
Whoa.
Works out. Okay? Agreed? Okay, what about then, what about that guy? Oh, it's a little different. Talk to me algebraically here. This is good. You get to really kind of think. The first time you're doing this stuff, it's always kind of fun in a way. You get to kind of think about the process. Yeah.
I'll make the A's equal 1.
Okay, so what do you reckon? So what's the algebra? So what Tyler's suggesting is that's a problem, right? And that's a problem. That looks different than what we had last time. Okay? I want you to notice something though. If this is going to be a circle, do those both have to be 2's? Or both have to be, do they have to be the same number? They do. They do. If we have time, I'll show you, I'll graph something and show you why. But if you look at the standard form equation of a circle, notice that it doesn't allow for there to be different numbers in front of the x's and y's, does it? Right? Would you agree that if I were to expand that out, I'm going to get an x squared there, aren't I? For sure. And I'm going to get a y squared there for sure. And so the only way that I could get different numbers in front of the x, I mean, I could get numbers other than 1 in front of the x squared and the y squared is if I multiplied both sides of the equation by something, right? So then, what does that mean in terms of that problem? Divide by 2, right? That's all I've got to do. Evidently, somewhere, if we imagine that we had started with the standard form and gotten to this equation, in addition to expanding it out, I would have had to have multiplied both sides by 2 at some point, right? Does that make sense? So yeah, I've got to just divide everything through by 2. What if I get fractions? Who cares? They're fractions, right? I've got to have a 1 in front of the x squared, just like we did in Module 3 when I complete the square, right? So we'll divide both sides of the equation through by 2, and then what do I get? Let's go ahead and arrange this in a convenient form while we're at it. What's it going to look like? X squared
Plus 8x.
plus, well, oh yeah, you're right. Duh. Plus 8x, good. Okay, leave a space, right? Leave a space because we're going to add another term there. What about the y's?
Squared. Minus 6y.
Minus 6y, leave a space. And then here we would have had 16, but we'll move it to the other side and make it negative 16, right? Okay, now you do it. Finish it up. I want to show you, I'll give some credit to Ruby on this too. I want to show you Desmos. This is, and I think I'm actually, okay, listen, we don't have much time. So Desmos is an online graphing calculator. And I understand in talking to some people who kind of know on the inside about what's going to happen with the new Smarter Balanced Assessment and maybe even like SATs and things. It's likely that the Desmos calculator is going to become the standard calculator for all standardized tests. And it's free and it's awesome. I mean, it's actually, I think it's nice to have a graphing calculator. I really do. But this is one that you'll use a lot, and it does everything a graphing calculator does, only some things better. Like, for example, a graphing calculator, it's hard to graph a circle. Graphing calculators typically only want to graph functions. And so you can't really put something in that's going to not be a function, like a circle, where it violates the vertical line test. But if you go in Desmos, if you pull up Desmos, and I think what I'm going to start doing is just linking to this on the questions. So you can just go to a link, and then it'll take you right to Desmos in another window. Like if I want to put in something like, let's just say, the quantity, I'm not very good at this yet, x minus 2 squared plus the quantity y minus 3 squared equals 9.
On this, you can actually use the equal button, like,
Yeah,
because on a graphing calculator you can't do that.
right. I mean, look what it does. It gives you the circle, right? Okay, now let's explore something though. Let's explore what would have happened if I would have put a different number. Like in this case, we have a 1 in front of the x squared and the y squared if I expand this, right? What do you think is going to happen if I put, someone make a guess, if I put like a 2 in front of that one? What do you think is going to happen? What's going to happen to the circle, do you think?
It's gonna be an oval.
Yeah, well, and what's our math name for an oval? It's going to become an ellipse, right? Okay, see that? So if I make the y, if I make the y something like 0.5, it makes it a more eccentric ellipse, meaning skinnier. Okay, more elongated. Okay, pretty cool. And you can do statistics stuff on here too. I just tried it the other. It works pretty well, pretty easily. I'll show you how to do that some other time. But this is kind of get used to this. Bookmark it in your Google account. It's really cool.